சார் பிஎம்ஆர்எஃப் இது இருக்குல்ல NPTEL இருக்குது லெக்சர் எடுக்கணும்.
ஓகே ஓகே நெட்வொர்க் வருதா? சரி.
இல்லை போதும் சார், போதும் சார். So let's start with week 8. This will be the last week for the course, problem solving session of 8th week on mechanical measurement system. And this week deals with sound measurement and the week 8 portion basically. So we'll see the questions related to that. So first we'll see some MCQs and then some problems related to the week 8. The first question is, a quantitative estimate of density changes can be made by, so a quantitative, not a qualitative, a quantitative estimate of a density change can be made by A. Interferometer, B. Shadowgraph, C. Schlerin system, D. Any of the above. So to change, to see the density change, and you have to calculate how the density changes, so you need to quantify the value. So how that is given by one of the equipment. So the options are interferometer, shadowgraph, C. Schlerin system, D. Any of the above. So the answer is A. Interferometer. If you see in the interferometer, the fringes are formed in interferometer, while the other gives you contrast in image or illumination. So in interferometer you can quantify based on the number of fringes, it will give you the variation in density. So as a reference, you have a reference fluid and you have density at the zeroth this thing. If you consider that, with respect to that how much the density varies, you can calculate based on the number of fringes, that you can quantify. But the others will give you a difference in the illumination, so that can give you qualitative information of what is happening, how is the density is varying. So B and C, shadowgraph and Schlerin system, will give you a qualitative estimate of the density variation, while a quantitative density variation can be inferred from the interferometer. So the answer is option A. So moving on, the next question is, which of the following optical device is used for visual studies in turbulent and compressible flows where the density gradients vary rapidly? So the question is, which of the following optical device is used for visual studies in turbulent as well as compressible flows, turbulent and compressive flows, when density gradients vary rapidly. So density gradients are varying rapidly. So in that case, which type of optical device can you use? So A. Interferometer, B. Shadowgraph, C. Schlerin system, and D. Any of the above. So the question is, yeah, optical device for having a rapid change in density gradients and are used for both turbulent and compressible flow studies. So in that case, the answer is option B, shadowgraph. So shadowgraph can be used in this case, and that will give you a better study compared to the others. So next question is, ORSAT apparatus is meant for estimating. ORSAT apparatus is meant for estimating. So yeah, it's mostly used in this is used in pollution measurement and all. So what kind of the apparatus is used in estimating what kind of? So A, volumetric analysis of the flue gas, B, direct determination of nitrogen in the flue gas, C, ash content of solid fuels, D, calorific value of solids or liquid fuels. So we have three options. ORSAT apparatus is meant for estimating. The first one is volumetric analysis of flue gases. B, direct determination of nitrogen flue gas. So first is analyze the flue gas. The second is say you determine the nitrogen in the flue gas. C, ash content of solid fuels. If you say you burn coal or something, the residual content. So they are measuring that. Or D, calorific value. Calorific value is the amount of energy you get from burning a liquid fuel or a solid fuel. So that is a calorific value. So which is can be measured using the ORSAT apparatus. We know that ORSAT apparatus measures CO2 and CO2 content in the flue gases. So in this case, the option is answer A, volumetric analysis of the flue gas. It does a volumetric analysis of the flue gas. Next, sorry, the answer is not A same. I'll remove this. The previous one, the answer of Orsett apparatus is meant for estimating is volumetric analysis of flue gas. Answer A. The next question, in Orsett apparatus, oxygen is absorbed in A. Cuprous chloride, B. Potassium carbonate, C. Dilute potassium sulfate, D. Alkaline solution of pyrogallic acid. So Orsett's apparatus, if you remember, we have three uh, solutions or setups to absorb individual gas component. So you have potassium hydroxide, then potassium hydroxide plus pyrogallic acid, so alkaline solution of pyrogallic acid, and then cuprous chloride. You have three setups, and before that also you will have some filtration system will be there. So this will absorb each of the component of the flue gas. So in this case they are asking which of the solution absorbs oxygen. So the answer is option D, alkaline solution of pyrogallic acid. So alkaline solution of pyrogallic, KOH plus pyrogallic acid, uh, potassium hydroxide plus pyrogallic acid will absorb oxygen. If you see potassium hydroxide or KOH will absorb carbon dioxide, and cuprous chloride will absorb carbon monoxide. So in this case the oxygen is asked, so it's option D, alkaline solution of pyrogallic acid. So moving on, we have the device extensively used for in sound measurement systems are, so the device which is extensively used for sound measurement are, so the device which is extensively used for sound measurement systems are A. Capacitor microphones, B. Carbon microphones, C. Dynamic microphones, and D. Vibration pickups. So the device extensively used for in sound measurements are, so you have four options. So the answer is option D, vibration pickup. So vibration pickup is just like the electromagnetic transducers which are used. So these are widely used for measuring sound measurement systems, or the microphones which are generally used. So these are vibration pickup types. So the answer is option D, vibration pickup. Moving on, which of the following statement about electromagnetic microphone is true? So you have four options, and we have to select which one is true for electromagnetic microphones. So A, they are they are not self-generating. So if it's not self-generating, it means it has to absorb some power. You have to give an external power. B, sensitivity of electromagnetic microphone is poor. C, frequency response is poor but linearity response is excellent. And D, both frequency and linearity response is poor. So for electromagnetic microphone, the answer is option D, both frequency and linearity response is poor for electromagnetic microphones. If we see this electromagnetic microphones are self-generating, so option A is ruled out. Their linearity is not good, so the only option left is option D. So answer is option D. So you have next, capacitor microphones has excellent linearity and large dynamic pressure range. B, poor dynamic pressure range but excellent linearity. C, poor frequency response and large dynamic pressure range. D, poor linearity but good frequency response. I repeat, capacitor microphone, A, excellent linearity and large dynamic pressure range. B, poor dynamic pressure range but excellent linearity. C, poor frequency response and large dynamic pressure range. D, poor linearity but good frequency response. So in this case the answer is option A, excellent linearity and large dynamic pressure range. So microphones, they are for input and output relations are very good. So and the dynamic pressure range can measure for a larger pressure range. So the answer is option A. Which of the following flow visualization technique is an accurate system with no aberration? So which of the following we have three options, and which is good for gives an accurate system for flow visualization technique? So A, interferometer, B, shadow graph, C, Schlieren system, and D, any of the above. So the answer is option C, Schlieren system. So this gives a better accurate visualization. So next question is, you have a typical solid employed for the absorption process in gas sampling technique. A, which of the solid is used for absorption process in gas sampling? So A, activated aluminate, B, activated copper compound, C, activated carbonate, and D, activated chlorine. So in this case the answer is option A, activated aluminate. So activated aluminate is used in gas sampling. These are all theory questions. We'll see some numericals also. Next question, we have in Orsett apparatus, carbon dioxide is normally absorbed by. So as I said earlier also, in Orsett apparatus we have three solutions to absorb separate fluid gas components, and you have potassium hydroxide, you have alkaline solution of pyrogallic acid, which is potassium hydroxide plus pyrogallic acid, and then you have cuprous chloride. So three is separate columns are there. So this potassium hydroxide will absorb oxygen, carbon dioxide. You have alkaline solution of pyrogallic acid will absorb oxygen, and cuprous chloride will absorb carbon monoxide. So in this case they have asked for carbon dioxide, so in this answer is option A, potassium hydroxide. So we'll see some numerical. We have a Seibold viscometer which is used to measure the viscosity of a certain motor oil. The time recorded for drainage of 60 ml is estimated at 183 plus or minus 0.5 seconds. So I hope Seibold viscometer is, you have a vessel of fixed dimensions, and you let the fluid flow and you measure the time. So using that you find out the viscosity. So in this case the time recorded is 183 plus or minus 0.5 seconds for the 60 ml of the motor oil to drain. So they calculate the flow following percentage change in uncertainty. So first you have to calculate the percentage change in uncertainty of nominal viscosity, and then percentage change in uncertainty of the viscosity. First you have to find out the nominal viscosity, and then you have to find the change in uncertainty of the nominal viscosity. So you have to find two. First we have to calculate viscosity, and then the percentage change in uncertainty. So you have to solve it like this. So we know that it takes 183 seconds, and this is the relation to calculate viscosity for a Seibold viscosity meter, which is 0.002370 minus 1.93 by T into 10 power minus 3 into 0.092903 meter square per second. So that is the relation. So if you substitute that time value in the given expression, so time is 183 seconds, so we get the viscosity as 3.92 into 10 power minus 5 meter square per second. This is 10 power minus 5, so 3.92 10 power minus 5, and in the question we asked nominal viscosity in 10 power minus 5. So it will be option A, 3.92 into 10 power minus 5. That is a nominal viscosity. I repeat, your viscosity can be calculated using the relation for a Seibold uh, viscosity meter, which is the nominal viscosity equals 0.092903 into, that's the constant, multiplied by 0.00237 times t, which is the time, minus 1.93 by t into 10 power minus 3. So that's the relation. We substitute time and we calculate the nominal viscosity, which we get as 3.92 into 10 power minus 5 meter square per second. And then we have to calculate the percentage change in uncertainty. So in this case, we know the viscosity relation. So, and we know the uncertainty in time. So dou v by the uncertainty in viscosity will be dou v by dou t into uncertainty of time. This is just if you recap of the uncertainty relation episode. If you see in the so dou v by dou t into wt. Wt is the uncertainty in time. So we know v, the nominal viscosity relation. We differentiate this with respect to time, and then we get 0.00237 plus 1.93 by t square, because this is 1 by t, and minus becomes plus, into 10 power minus 3 into the constant 0.092903. In this case, we substitute time 183, and we also know wt as per the equation. Question is given as plus or minus 0.5 seconds. So wt is uncertainty is 0.5 seconds. So we substitute uncertainty of time as 0.5 in this equation, and time as 183. On substitution, we get the uncertainty in nominal viscosity as 1.12 into 10 power minus 7 meter square per second. This is just the uncertainty, but the question asks for percentage change. So we divide by viscosity, which we calculated previously, which is 3.92 into 10 power minus 5, and multiplying it by 100, we get 0.287. So 0.287% change in uncertainty. So the answer is option B. So I repeat, we have the nominal viscosity relation, we substitute time and we find out viscosity. Then a percentage change in uncertainty is, we know the percentage uncertainty of time. Then uncertainty of viscosity is dou v by dou t, because we know v, we differentiate that with respect to t, into uncertainty of time. We substitute the time and uncertainty of time, and we get uncertainty of the viscosity. We know viscosity, we calculate the percentage change in viscosity, which is 0.287. I hope this is clear. Okay, then moving on. So the question answers are answer option A and option B respectively. So the next question is, you have an individual sound pressure level measured at a particular location from two machines are noted to be 79 decibel and 82 decibel respectively. So the noise level with both the machines operating together is given by, so we have individual sound pressure level measurement of two machines, which is 79 and 82. Then if you are operating it combined, so what will be the noise level? That's the question. So the options are given. So if you say that x and y are the sound pressure levels of two machines, then a combined noise level will be 10 log 10 anti-log of x by 10 plus anti-log of y by 10. This is the combined relation. Then we have to substitute just x and y relation. So in that case, we'll have 10 log 10 anti-log of 78 by 10 plus anti-log of 82 by 10. It's just, if you see, it's just based on the pressure and intensity relation of the decibel calculation. So from there we'll get this relation 10 log 10 of antilog of x by 10 and antilog of y by 10. It's just the intensity addition. So if you substitute x is 78 and y is 82 for the two machines, then you get 10 log 10. First expression value is 22.16, and second the total is 22.16 into 10 power 7. This is 10 power 7. So the answer is 10 into 8.3456, which is 83.456 decibel. So the combined pressure noise level is 83.456, which is our answer, option A. I hope this is clear. Okay, then moving on. Moving on, we have a certain microphone which has an open circuit sensitivity of 80 decibel, referenced to 1 volt for sound pressure excitation of 0.1 pascal. So we have a microphone which has sensitivity of 80 decibel, which is referenced at 1 volt, and pressure excitation of 0.1 pascal. Calculate the voltage output when exposed to a sound field of 100 decibel. So we'll see how to solve this problem. This is minus 80, open circuit, minus 80 decibel, and reference is 1 volt, pressure excitation is 0.1. We have to calculate the voltage when it is 100 decibel. So sound pressure is calculated as 20 log 10 pressure by P1 by P 0. Here we know uh, so for P 0 value of 2 into 10 power minus 4, we have decibel 100 decibel. We have to calculate for the pressure value of 100 decibel. So we know the relation, and we know P 0 value also, the standard value, and sound for 100 decibel we need to calculate the pressure. From pressure we will calculate how much voltage it will generate. So for 100 decibel, P1 value will come out to be 20 pascal. Then as per the question, we know for an excitation of 0.1 pascal, the voltage is 1 volt, and for the sound noise level is minus 80 decibel. So in this relation, for reference voltage can be calculated as minus 80, which is the noise level, equals 20 log 10 the excitation EMF or voltage generated by the reference EMF. So in this case the reference EMF is 1 volt. So the excitation EMF for required for minus 80 decibel is 10 power minus 4 volts, or 0.1 millivolt. So for 0.1 pascal, the EMF generated is 0.1 millivolt. So in a similar case, as this gives you a linear relation, for 20 pascal is excitation into 10 power E into for 20 pascal you multiply it by the EMF generated, you will get 20 into 10 power minus 4 volt, which is 2 millivolt. I repeat, in a sound pressure measurement, we have first we have been asked to calculate the voltage generated for 100 decibel noise level. So we first calculate the pressure generated for the 100 decibel. So we know that sound pressure level for 100 decibel equals 20 log 10 P1 by P naught, and P naught is 2 into 10 power minus 4. We substitute that, and we know that the noise level is 100 decibel. We substitute that as well, and we calculate P1 value. P1 is 20 Pascal from solving the relation, and we know that for 80 decibel we need to calculate for 0.1 Pascal. Uh, the reference voltage is 1, so the excitation voltage will be a noise level equals 20 log 10 the excitation EMF divided by the reference EMF. uh, so that after solving we get the excitation value is 10 power minus 4 volts, or zero point 0.1 millivolts. So point you for 20 Pascal, we have to multiply with the excitation voltage. So there we'll get 20 into 10 power minus 4, which is 2 millivolts. So the answer is option A. So moving on, we have a pressure of sound measured at a distance of 1 meter from power hammer is stated as 12 Newton per meter square. So from pressure, the sound measured at distance of 1 meter is 12 Newton per meter square. So we have to find the corresponding sound pressure level in decibel. It may be presumed that the pressure at the threshold of hearing is 0.002 microbar. P naught value is 0.0002 microbar. You have to find the noise level. So we just convert the pressure into in terms of bars. We have 12 Newton per meter square, so which will come out to be 120 microbar, or uh, 1 bar is 10 power 5 Newton per meter square. We'll get 12 into 10 power minus 5 bar, or to 120 into 10 power minus 6 bar. So my 10 power minus 6 is micro, so 120 microbar, and the reference pressure is 2 into 10 power minus 4 microbar. So both are in microbars. So now we substitute for noise level equals 20 into log 10 P1 by P naught. We know P naught is 2 into 10 power minus 4, and P1 value is 120. We substitute both, and we get uh, this noise level as 115 point dx. As intensity is inversely proportional to distance square, and distance is 1 meter, so this will remain same. So the sound pressure level at 1 meter will be same as 115.56 decibel. So moving on, the pressure of sound measured at this is option A. So next question is, we have a guarded hot plate apparatus which is used to measure the thermal conductivity of a metal having uh, thermal conductivity of 50 watt per meter Kelvin, and the thickness of the specimen is 0.125 plus or minus 0.002 meter. So thickness is given, thermal conductivity is given, and the heat flux may be measured within 1%. So the uncertainty of heat flux measurement is 1%. When asked to calculate the accuracy necessary on the temperature measurement in order to ensure an overall uncertainty in the measurement of K. So overall uncertainty of measurement of K should be limited to 5%. So the what should be the temperature uncertainty? And Further, they say if one of the plate temperature is nominally 300 Kelvin, so one of the plate temperature is given as 300 Kelvin, calculate the nominal value of the other plate temperature and the tolerable uncertainty in each temperature measurement. So heat flux is given as 20 to 1000 watt per meter square, 20,000 watt per meter square. So K is given, thickness is given, and heat flux is given. Temperature, one of the temperature is given, so we can find the other temperature as well using the Fourier's law. And then uh, we have been asked to also calculate the uncertainty in temperature measurement, for which uh, uh, the uncertainty of K should not exceed 5%. So uncertainty of K is given, uncertainty in thickness is given, uncertainty in each heat flux is given. So only remaining is temperature, that can also be found. So we'll see how to solve this. We know from Fourier's equation, Q is uh, Ka delta T by delta X. So we write this in terms of thermal conductivity. So Q by A into delta X divided by delta T. So Q by A is the heat flux. Q is heat transmitted. In this, Q by A is heat flux. So uh, we know that K by K is uncertainty of K by K is 5%. So it will be 0.005. And then we also know that WQA by Q by A is 1%. So we express all, we find out W. If you see the uncertainty for product rule, that can be written as per this expression, WR by R equals dou R by dou X1 whole square, W1 by R, so on. In this case, R is the K value, the expression which I have to calculate. So WK by K, which is already known, so the rest of the expression we have to calculate. So the dou K by dou X1, the variables here are heat flux, delta X, the thickness, and then temperature. So those are the relation. So we have to find out the derivatives with respect to K individually, and also the uncertainty of the variable divided by K. So those are required. So initially we calculate the uncertainty by K, or with respect to heat flux. We know uncertainty of heat flux, which is given as 1%, and divide by K. So we substitute the expression for K, and we will get simplified value as 0.01 delta T by delta X. Similarly, we find out W for delta X, uncertainty in thickness, divided by K. So the relation is the simplified expression is 0.002 delta T divided by heat flux into 0.125. Similarly, we calculate it for temperature as well. So we know all the values of heat flux and the delta thickness, uncertainty, everything. So we saw, and as also we know we have to calculate the derivatives, and once we multiply the WK uncertainty by K into the derivative of the respective variables of K, then we will get a simplified expression. So simplified expression will be WK by K is 0.05 into, we have the whole relation, the first term, dou R by dou X1 the whole square into W1 by R the whole square, will come out to be 0.01 whole square. Similarly, the next one will be 0.002 by 0.125 the whole square, and third one will be W by delta T by delta T the whole square. This whole will be raised to power half. So in this case, we have to solve for W delta T by T, uh, or delta T. So in this case, that will come out to be 0.0146 or 1.46%. So the uncertainty for temperature measurement will be 1.46%. Then the next equation is you have to calculate the temperature of the other plate. The first plate is given as 300. You have to calculate the temperature of the other plate. So we know the expression for the delta T. You have to just reshuffle the first expression for from the Fourier's law, and then we'll get delta Ts heat flux into delta X divided by thermal conductivity. We know all the values. Heat flux is 20,000 watt. Delta X is given as 0.125 and K is 50. On substitution we'll get 4.16667. So we know the temperature uh, of the other plate. So now we need to the question says calculate assuming sorry calculate the nominal value of the other plate temperature and the tolerable uncertainty in each temperature measurement. So tolerable uncertainty we have to calculate. So in that case uh, for temperature delta T is T1 by T2 T1 T2 minus T1 delta T. So we know that relation. So from this Wt by delta T we have already calculated. So for each temperature measurement we have to calculate. So Wt by delta T equals same expression as is written for temperature. So in this case for differentiation of delta T with respect to T1, T1 and T2 are the variables both for both the plate temperatures. So we are measuring temperature of the both the plates. So uncertainty in temperature is what we needed. So from the expression we can simplify this delta T1 and delta T2 on substitution we'll get as W delta T as W T1 square plus W T2 square, the whole raised to power 1 by 2. So both W2 and WT2 will be same, so will come out to be 2. So 2 times root 2 times WT1, because we have raised to power 1 by 2. So root 2 WT1 or WT you can say. So we know W delta T. We from this relation we can find out the uncertainty in temperature measurement, which will come out to be 1 by root 2 times W delta T. This W delta T is 0.0146. So we substitute that, and we also know delta T is 4.1667. So we multiply W delta T into T. So that will this is in percentage. So we multiply by T to get W delta T. So 0.707 is 1 by root 2 into W delta T is 0.0146 into delta T 4.1667, which will come out to be plus or minus 0.043 Kelvin. So this is the uncertainty in temperature. So I hope this is clear. This is just simple expression using the uncertainty measure law. So if you use that, we can easily find out the others. First we start with K. The question says limit K to 5% to, so that we measure and measure the W delta T. What is the uncertainty in W delta T? So using that and the uncertainty analysis, we calculate W delta T using the expression, and we substitute all the derivatives and the corresponding uncertainty of each variables, and then we find out W delta T is 1.46%. Then we find out the other question was find out the temperature and the uncertainty in temperature. So we find out delta T. Using that we find out the temperature of the other plate, and then we know delta T is T1 minus T2 or T2 minus T1, and from there we, using same uncertainty analysis with the expression of delta T, we calculate the uncertainty in temperature, which comes out as 1 by root 2 W delta T. I hope this one is clear. So the next problem is a sample is collected at a rate of 0.05 feet cube per second for a period of 45 minutes through a filter area having a diameter of 1 inch. As a result of the sample collection, the light transmission of the filter paper is reduced from 80 to 55%. Calculate the COH. COH is the coefficient of haze. So we have to calculate the coefficient of haze, and they say sample. Uh, the main thing is it's the filter paper which is used. That light transmission is reduced from 80% to 55%. So in this case, we know that coefficient of haze is calculated as optical density divided by zero point 0.1, and optical density is expressed as log 10 I by IO, or intensity by intensity naught. This I by IO can be also be written as 1 by T frac. This is the fractional transmittance. T frac is the fractional transmittance. So this fractional transmittance is how the difference, how much the light is getting reduced. So here they have said how much the fraction is. We have to calculate the fraction. They have said that the transmission is reduced from 80% to 55%. So free T frac is calculated as uh, uh, the reduce T2 or by T1. So it has reduced to 55% divided by 80%. Initially which was in 80%, and it has reduced to 55%. So that T frac can be calculated as 0.55 divided by 0.8, which will give you 0.6875. So from there, T frac is 0.6875. We substitute this in the coefficient of haze relation. So we will get coefficient of haze as 100 log 10 divided by 1 divided by 0.6875, which is the T frac. So it will come out to be 16.272. So that is the coefficient of haze. I repeat, in this question we have said that the light transmission in the filter paper has reduced from 80% to 55%. So coefficient of haze can be calculated using, we know coefficient of haze is optical density divided by 0.1. So that will come out to be 100 log 10 I by IO. Optical density is log 10 I by IO. That's the intensity of light transmitter, which can also be I by IO can be also be calculated written as 1 by T frac, for the fractional transmittance. In the question which is it's given as the transmittance is reduced from 80% to 55%. So T frac is 55 by 80, or 0.55 by 0.8, which will give you 0.6875. So we substitute that in T frac, and we calculate coefficient of haze as 16.272. So that's all for today's problems. If you have any doubts, you can ask me. So as there are no questions, we'll end the session.